In the last lecture, we seen that when theorem, let K be an normal extension of a field F with characteristic 0. Okay, then T is the what subfield of K containing F. T be a subfield of K containing F. Then we prove that T is the normal extension of F if and only if sigma of T contained in T. Okay, that is T is invariant under sigma for all sigma belongs to GK. Okay, so today we will see the next point, Galois group. What is the Galois group? Okay, wait a minute. The next definition is Galois group. Galois group. The definition. Let f of x, this f of x, be a polynomial in capital F of x, and let capital K be its splitting field. Capital K be its splitting field. That means this f of x can be written as into the in the form of product of linear factor on K. Okay, let K be the splitting field over F. The Galois group is nothing but the Galois group of f of x of f of x is the group of GKF, okay, of all those automorphisms of K, those automorphisms of K which leaves every element of this capital F fixed. Okay, the Galois group is nothing but what? The GKF. The GKF is also called as Galois group. But here the one more condition is there. This K be a splitting field of some polynomial f of x over this base field. Okay. तिथे काय होता फक्त तुम्ही तुम्हाला f दिला होता f, and this one is k. K is the extension of f. Then set of all those automorphisms of K which leaves every element of f is fixed. Okay, then that group is called GK. So here K is the extension of f, but K is the splitting field of f of x, where the f of x belongs to capital F of x. Okay, हा जो extension आहे तुमचा K, this extension of K, f, that K must be a splitting field of some polynomial over f of x, capital F of x. Okay, this K is the splitting field of some polynomial over this f base field. Okay, and that group of all automorphisms is nothing but Galois group. Okay, is it clear the definition? Okay, थोड़ा speed लगेगा आपल्याला syllabus पूर्ण cover करायचं अजून. Okay, now if capital K is an extension, capital K is an extension of field F, capital F, then an automorphism of K which leaves every of capital F fixed is also called an F automorphism of K. An F automorphism of K. Okay, what does this mean? If K is an extension of the field F, then an automorphism of K which leaves every element of F is fixed, then it is also called as F automorphism of K. ओके, या ग्रुप ऑफ ऑटोमॉर्फिझमला काय म्हणतो आपण? F automorphism of K. Okay, every element of this group, if sigma belongs to this GKF, then this sigma is what? F automorphism of K. That means this sigma leaves every element of F is fixed. Okay, where this sigma is automorphism over K. Okay, any doubt? Okay, now we have one theorem.
No, sir.
Look at this theorem. Okay, हा theorem खूप मोठा आहे. सो लक्ष द्या, जवळपास 40 ते 50 मिनिट लागतील आपल्याला. Theorem. The Galois group of a polynomial. The Galois group of a polynomial over a field of f of characteristic 0. Okay, of characteristic 0 is isomorphic. Is isomorphic to a group of permutation of its root. Okay, what is the permutation group? Do you know? माहिती आहे का what is the permutation? Group of permutation. The Galois group of
Yes,
a
sir.
polynomial over K over a field F with characteristic 0 is isomorphic to a group of permutation of its root. Okay, suppose this f of x be the polynomial over the capital F. Okay, now if K is the extension of F, then this one is what? Galois group of f of x, where K is the splitting field of this f of x. It's isomorphic. Isomorphic group of permutation, which is denoted by P. Okay, हा P कोणावर डिपेंड केलेला आहे? Permutation group, permutation of its roots. Okay, suppose these are the R roots of this f of x. Okay, suppose this set x, yes, is there. Suppose alpha 1, alpha 2, up to so on, alpha r. These are the R roots. Okay, what is the permutation? 1, 1 onto function defined on this set. Okay, so how many permutations are there? We can define on this set. Suppose x is equal to 1, 2, 3. What is the order of permutation of 3 factorial? Yes, 3. Is it correct? Okay, 3 factorial. 3 factorial.
Yes, sir.
Type permutation 1, 2, 3. 1, 2, 3. Okay, identity point. First one is identity mapping. Wait a minute. A base clear how I can. This is the identity mapping. 1, 2, 3. 1 maps to 2, 2 maps to 1. 3 is fixed. Next one, 1, 2, 3. 3 fixed, 2. So 1 maps to 3, 3 maps to 1. Okay, now 1, 2, 3. Now 1 is fixed, 2 maps to 3, 3 maps to 2. Okay, this is 1, 2, 3. 1 maps to 2, 2 maps to 3, 3 maps to 1. Okay, 1, 2, 3. 1 maps to 3, 2 maps to 1, 3 maps to 2. Okay, 1, 3, 2. Okay, so these are the 6 permutations we can define on the set of x, on the set x. Okay, that is 3 factorial, which is equal to 6. Now here the set S contains all the roots of f of x. So how many elements we can, how many permutations we can define? That is 1, 1 onto function r factorial. Okay, but आपले हे सगळे r factorial permutation घ्यायचे नाही. So P be the set. Okay, पुढे कळेल तुम्हाला एक्झाम्पल. Okay, this is the set of permutation. Group of permutation. Okay, defined on this set x. Now look at it. Proof. So we have to prove that that group of permutation of root is isomorphic to GKF. Okay, the GKF is isomorphic to what? Permutation of its roots. Okay, now look at the proof. The Galois group of the polynomial over a field F with characteristic 0 is isomorphic to group of permutation of its roots. What is Galois group? GKF, where K is the extension of F and K be the splitting field of some polynomial f of x over F. Okay, now write down all the given things. Let f of x be a polynomial. Be a polynomial over a field capital F. Okay, of characteristic 0. Okay, now let capital K be a splitting field. Okay, capital A, K be a splitting field of f of x over capital F. Okay, then K is the normal extension of F. Okay, we proved that if K is the splitting field of f of x over f with characteristic 0, then that K is normal extension of F.
F.
So then capital K is normal extension of capital F. Okay, therefore the Galois group GKF of f of x is a finite order. Okay, therefore the Galois group group GKF of this polynomial f of x is of finite group. Why this is finite? Because degree of k over n is equal to what? K over f is equal to what? N. Okay.
N.
Degree of k over f is what? Every normal extension is finite extension. So this is k over f is equal to n. Okay. See. Now by corollary we have by
Degree
corollary
is equal to order
we
of
have
GK.
degree of k over f is equal to order of g k f. Okay. Any doubt? If k is normal extension of
No, sir.
capital F. Okay, so here the degree of k over f is n, and the Galois group gk of f of x is of finite group. Now let sigma 1, sigma 2, sigma 3 up to so on sigma n be the n distinct automorphisms of GKF. Okay, let sigma 1, sigma 2 up to so on sigma n with the n distinct automorphism of GKF. And suppose f of x, this polynomial, has only m distinct roots in K. Okay, suppose the degree of f of x is n, then it has m or m plus 1 greater than m. We don't know. Okay, so this these m roots are distinct roots of f of x. Okay, look at it. Suppose this is the f. This one is capital K. Okay, f is k is the normal extension of field f. Now it is possible that f of x have uh, roots. We don't know, but these m roots are distinct. Okay, write down. It is possible. It is possible that f of x, this polynomial, may have multiple roots. Okay, but these m roots are distinct roots. So let define a set, that set of all the roots. This is suppose alpha 1, alpha 2, up to so on, alpha m. These are the roots of the f of x. Okay, be the set of m distinct roots of f of x in k. Okay, why? Because k is the splitting period of f of x. So these alpha 1, alpha 2, up to so on, alpha m, these are the elements of k. Okay, so suppose this is the set. Yes, alpha 1, alpha 2, all are the roots of f of x. Okay, n roots are there. Okay, but we don't know that whether the alpha, here सर्व alpha कशातून आहेत, alpha 1, alpha 2 are the elements of k, but some of them they may have in f also. Okay, we don't know. Suppose this is the set S. Okay, any doubt? Some of the maybe
No, sir.
belongs to this field F. Okay, but all the roots are belongs to K, which means some of them are belongs to F and some of them are outside the F. Okay, so this is the set X, set S, alpha 1, alpha 2, up to so on, alpha m. Suppose इथे तुमचा alpha 4 आहे, alpha 5 हा आत आहे. Okay, two roots are belongs to F. Suppose, okay, but we don't know it. Now let capital P be the set of all those permutation on S which change. नीट लक्ष द्या काय सांगतो. हे स्टेटमेंट खूप महत्त्वाचं. Set P be the set of on S which change only those elements of S which are not in F, which are not in capital F. Okay, what is the meaning of this one? That is, which leaves every element of this capital F fixed. Okay, now look at it. How many elements are there in set S? M elements. Okay, so we can define
M
m
elements.
factorial permutation, that is 1 1 and on 2 mapping on the set S. Okay, but P be the set of those permutation which leaves every element. Okay, which leaves, if the element belongs to F, then it must be fixed. For example, S3. What are the elements of S3? Suppose this is the set. Yes. Okay, 1, 2, 3. Okay, and suppose this one is the field, our field. What are the S3 set? 1, 2, 3.
One.
Okay, first one. 1, 2, 3. समजा तुमचे 1 2 3 हे तुमचे roots आहेत. Instead of alpha 1, alpha 2, alpha 3, alpha m, 1 2 3 are the roots. Okay, and 3 belongs to set K as well as set as well as field F. Okay, so here 1 maps to 1, 2 maps to 3, 3 maps to 2. Okay, 1 2 3, 1 maps to 3, 3 maps to 1. Okay, 1, 2, 3. 3 maps to 3, 1 maps to 2, 2 maps to 1. Okay, 1, 2, 3. 1 maps to 2 maps to 3 maps to 1. 1, 2, 3. 1 maps to 3, 2 maps to 1, 3 maps to 2. Okay, so these are the 6 elements belongs to S3. Okay, this is the all permutation. Okay, now set P with the collection of those permutation which leaves this 3 is fixed. म्हणजे आम्ही पी सेट मध्ये कोणते एलिमेंट घेतले जो तुमच्या 3 ला 3च ठेवतोय, हा 3 ला 3च ठेवतोय, म्हणजे हा तुमचा कशात आला टी मध्ये आला. 1 2 3 1 2 3. ओके, अजून 3 फिक्स कुठे आहे इथे. ओके, 1 2 3 2 1 3. ओके, अजून 3 कुठे फिक्स आहे काय नाही. ओके, सो पी मला सेट करायला एक आयडेंटिटी मॅपिंग and 1 2. Okay, now this one is what subgroup of this S3, is it correct? Okay, so
Yes, sir.
look at here. So here, wait a minute. P with the set of those permutations on S, okay, which change only those elements of S which are not in F. Look at here. Suppose here 1 and 2 is not belongs to F. So these are the two permutation which change which are not in F. Okay, wait a minute. Okay, identity तर असणारच आहे तुमचा. Okay, ह्या definition नुसार which leaves every element of F is fixed. So here 3 belongs to F. So it means P contains this one. Okay. So here 3 belongs to F. So 3 fixed here. 3 maps to 3, 2 maps to 1, and 1 maps to 2. So outside the F, 1 and 2 become changed. 1 maps to 2 and 2 maps to 1. So P contains only those elements, those every element of F is fixed. Okay. इथे 3 एलिमेंट घेतले, पण इथे किती आहेत एलिमेंट m. या m फॅक्टोरियल मधून असे एलिमेंट कलेक्ट करायचे. Let P be the set of those permutation on S which change only those elements of S which are not in F. Look at this one. This is F. This is set S, and this one is set K. Okay. So here the P is nothing but what? Subgroup of permutation. Okay. Subgroup हा ग्रुपच असतोच, म्हणजे हा काय झाला itself a permutation group. Okay. Any doubt? ही कन्सेप्ट समजली की पुढचा सोपा आहे समजायला.
No, sir.
Okay. Wait a minute. Let P be the set of those permutation on S which change only those elements of S which are not in F. That is, which leaves every element of F is fixed. Okay. Now, if this is not the part of theorem. Okay, this one and this one. If G1 and G2, if suppose this G1 and G2, okay, G1 and G2 are two elements of P, then G1 composition G2 will also be an element of P. Okay, because G1 composition G2 will also leaves element of capital F fixed. Okay, look at here. If G1 belongs to what? P. So G1 of A is equal to what? A. And G2 of A is equal to what? A. Okay. Then
A.
for all A belongs to F now. Okay, so G1 composition G2 of A is equal to what? G1 of G2 of A, which is equal to G1 of A, which is equal to A. So this implies P should be closed with respect to product of permutation. Okay, so this implies their set P is closed with respect to product of permutation. Okay, any doubt up to here?
No, sir.
So this implies the set P is a subgroup the identity 1 2. Okay, similarly here P is the subgroup of the group of permutation, the group of all permutation on the set yes. Okay, P will be the subgroup of the group of all permutation on set yes. But in the P, in the every element of P, the every permutation belongs to the set P, every element of F is fixed. That is 3 maps to 3 here. Similarly here, if suppose alpha 1 belongs to set F, then sigma of alpha 1 is equal to alpha. Okay, suppose the phi is permutation and alpha 1 belongs to this one, F. So phi of alpha 1 must be alpha 1. Phi of alpha 2 must be alpha 2 if alpha 1 and alpha 2 belongs to the set that field F. Okay, so here we prove that P is the subgroup of the group of all the permutation. And now we have to prove that the main theorem. The group, what is the group? GKF. Okay, is what? Isomorphic to group P. Okay. The set of those permutations, sorry, the set of all the automorphisms of K which leaves every element of it fixed. And in the P, the set of those permutations on set yes, which leaves every element of F is fixed. Okay. In that permutation, element of the root of that polynomial f of x, if the root is belongs to F, then it must be a fixed. Okay, if alpha 1 belongs to F, then okay, if suppose this sigma or phi with the permutation belongs to the set P, then phi must be fixed. Phi of alpha is with phi of alpha is equal to alpha for every alpha belongs to. Okay, now we have to prove that this is the isomorphic to group P. Okay, GKF is isomorphic to group P. That the mapping, there exists a mapping from this set to this one, which is 1 1 onto an homomorphic. Okay, now let the sigma belongs to GKF. Okay, sigma belongs to what? This set GKF. Sigma is the mapping from K to K. Okay, automorphism of K. And assume this sigma star be the restriction of sigma to Yes. This one is what? K. This one is what? K. Sigma is the mapping from K to K. And this one is what? Yes. This one is what? Yes. Hmm. Sigma star is the restriction of sigma to yes. So this is the sigma star. Okay, but sigma is equal to sigma star on what? Yes. So sigma is the continuation of sigma star. That means sigma star is the restriction of sigma here. Okay, and let sigma belongs to GKF and sigma star be the restriction of sigma to yes. That is, we have sigma star of alpha is equal to sigma of alpha for all alpha belongs to yes. म्हणजे काय हा sigma star and sigma are equal on set yes. Okay, what is set is alpha 1 alpha to all the roots of f of x. Okay, any doubt up to here?
No, sir.
Now, if alpha is a root of f of x in capital K, then sigma of alpha is a root of f of x in capital K. Okay, so alpha तुमचा कुठून आहे S मधून. Alpha belongs to set S. If you apply sigma on the on the set, if you apply on the alpha, the image of sigma of psi of sigma of alpha must be belongs to again set S. But set S is what? All the roots of f of x. Then we have sigma of alpha is also root of f of x in K. Okay, for this we have one theorem. या theorem नुसार root maps to root आहे पहा. F of A maps to okay if A
Yes, sir.
and B are the two roots. Hmm. What is the theorem? This one. If why this sigma of alpha is the root of f of x? Look at here. If E is an extension of capital F and f of x belongs to capital F of x. Wait a minute. Capital F of x and phi is an automorphism. Is an automorphism. Okay, is an automorphism of E, leaving every element of F fixed. Every element of capital F is fixed. Okay, then phi takes the root of f of x, root of f of x lying in E into the root of f of x in E. Okay, this theorem we proved in the last lectures. Okay, previous lecture we proved this one. Okay, look at this. What is the statement? If E has an extension of the field F, so here E is what? K. Okay. Now here F is F. Okay, if f of x belongs to f of x and phi is an automorphism, here phi is what? Sigma star. Okay, sorry, it's not sigma star. Sigma is an automorphism of K. So leaving every element of f fixed here, sigma. So sigma takes the root of f of x in E into root of f of x in E. Okay, so that means sigma of alpha is also root of f of x in K. Any doubt now? Okay, so
No,
therefore,
sir. No, sir.
therefore alpha belongs to yes. Okay, set of root of f of x. What is this? Set of root of f of x. If you apply sigma star on alpha, which is equal to what? Restriction of sigma. Na? So this is sigma of alpha belongs to yes. Okay. where this sigma belongs to G, K, F. Okay, so sigma star is a function from S to S. Okay, and further, this is automorphism. Okay, and sigma star are equal on what? Yes. So that means this is also an automorphism, not automorphism. This is 1 1. हा जर 1 1 आहे, automorphism आहे म्हणजे हा 1 1 आहे. So that implies this function is also 1 1. Okay, and if you define any 1 1 function on the finite set, okay, yes, it's finite now. If you define any 1 1 function on the finite set, then that function must be on 2. Okay, is it correct? एखाद्या फायनाइट सेटवर आपण 1 1 फंक्शन डिफाइन केलं की तो ऑटोमॅटिक ऑन 2 होतो. Okay, so further here sigma star is a function from S to S. Further, the sigma star is what? 1 to 1 function. That is 1 1 function. Since a finite set S is S is a finite set. Okay, yes is a yes is a finite set. Okay, therefore sigma star is 1 1. That implies sigma star is on 2. Is it clear? माहित आहे का हे definition?
Yes, sir.
If you define a function 1 1 function on the finite set, then it will become a on हा सेट आहे तुमचा. येस. ओके, समजा 3 एलिमेंट आहेत. ओके, हा ह्याला मॅप आहे, हा ह्याला मॅप, हा याला मॅप. ओके, हा सेट 3 एलिमेंट्स असतील तर ह्याच्यातही 3च एलिमेंट्स असतील. ओके, हा तुमचा 1 1 आहे. मग हा काय झाला? ऑटोमॅटिक ऑन 2 झाला की नाही? ओके,
Yes.
कधी?
Yes, sir.
If the set S is finite. Okay, for the infinite set we cannot say that. Okay, so on the finite set any 1 1 function must be on 2. So here the set psi star sigma star is the function from S to S. So sigma star is 1 1, so sigma star is also on 2. Okay, now any 1 1 on 2 function on this finite set becomes a permutation. Okay, so thus psi star is nothing but what? Permutation म्हणजे काय असतंच काय? 1 1 and on 2 function. Here sigma
One
star
one
is
on
1
two.
1 and on 2. So here sigma star is permutation. Permutation on yes. Okay, so since sigma star is a permutation, okay, look at this one, correct. Since sigma star is a permutation on what? Yes. Okay, and sigma star is sigma, okay, leaves every element. Sigma कुठून आला तुमचा? GK. Okay, sigma leaves every element of capital F is what? Fixed. Okay,
Fixed.
sigma leaves every element of capital F fixed. Okay, so this implies it follows sigma star also leaves every element, okay, element of capital F fixed. Okay, so any doubt? sigma is the permutation on F.
No, sir.
Okay.
No.
Sigma हा permutation on S आहे म्हणजे काय होईल? Okay, sigma is the permutation. Sigma star is the permutation on what? Set S. Okay, 1 1 and on 2 आहे. आणि समजा हा तुमचा अल्फा इथून आला F मधून. ओके, या फंक्शन इथून आला. तर तो काय करेल? Sigma star is equal to sigma is equal to what? Look at here. Sigma and sigma star both are equivalent on set. Yes. Look at here. Sigma star and sigma. Sigma star and sigma both are equal on set. Yes. Okay, आता yes आणि F मध्ये इंटरसेक्शन मध्ये काहीतरी एलिमेंट आहे जो डार्क केला आहे इथे. Suppose sum of alpha 3 alpha 4 are the elements in the intersection of S and F. So for that element, that sigma star also what? Element of
Leaves every element of F fixed.
F fixed. Okay. So hence by the definition of P, what is P? This sigma star belongs to P. Okay. Is it 1 1 hai, on 2 hai, that is permutation hai?
Yes, sir.
Okay. And every element of F is fixed. Okay. By the definition of P. Okay. Now we have, wait a minute. We have sigma of alpha is equal to alpha for all alpha belongs to F. Okay, sigma leaves every element of F is fixed. Okay. Now let define a mapping. Let psi be a mapping. Okay. Psi be a mapping from GKF to P. Okay, that is psi is a mapping from GK F. Okay, to P, set of all those permutations on S, which leaves every element of S is F is fixed. Okay, and this is what set of those permutations of K, which leaves every element of F is there also fixed. And if now we have to show that this psi is 1 1 on 2 and homomorphism. Okay, so let psi be a mapping from GK to P, defined as defined as psi of as a element kind sigma is equal to sigma star. Okay, sigma star belongs to here P. But what is sigma star? The sigma star is nothing but the restriction of sigma. Okay, for all sigma belongs to G, K, F. Okay, any doubt up here? Okay, in the next lecture we will prove this 1 1 onto an homomorphism. Okay, for today it is sufficient. Okay, mapping sigma star कशामुळे घेतले कळालंय? Sigma star is the restriction of sigma on S. Okay, and the sigma star is equal to sigma on S. And we have shown that the sigma star is 1 1 on 2. That is sigma star, and also sigma star leaves every element of F is fixed. That's why this sigma star belongs to P. Now we can define the function like this: psi of sigma is equal to sigma star. म्हणजे तुमचा इनपुट हा जी के मधून यायला पाहिजे आणि आउटपुट कशामध्ये यायला पाहिजे? P मध्ये. Okay, but what is sigma star? Sigma star is nothing but restriction of sigma. All sigma belongs to GKF. Okay, any doubt up to here? In the next lecture we will do this.
No, sir.
To that psi is 1 1, psi is on 2 and homomorphism. If you prove this three condition, then there is isomorphism. There exists isomorphism between GKF and P. Okay, the set of those all the automorphisms of K which leaves every element of F is fixed is isomorphic to the group of permutation. Okay, group of permutation, and the permutation defined on what? The roots of F of X. Okay. Any doubt up here? Okay. So thank
No,
you
sir.
for attending the lecture. You can leave now and join the ma'am's lecture. Okay. So thank you for once again. Thank you.